All right, let's continue talking about an introduction to organic chemistry, which is generally known as GOC or General Organic Chemistry. NCERT has a different name on it. You know what I'm talking about. I'm doing things in a way that is slightly different than NCERT because I feel this is the best way to learn organic chemistry. You need to revise all of these topics, right? So firstly, we'll look at how organic compounds are represented. You can figure out nomenclature by yourself. We will revise formal charge and why it's relevant, and we'll talk about resonance in this one. Later videos will have hyperconjugation, etc., etc. So a bit of a revision from chemical bonding. Two types of bonds, right? Sigma and pi. And if you remember, if you don't, check out those videos. Number of pi bonds in a carbon that's sp3 hybridized is 0, sp2 is 1, sp is 2. So C triple bond C, two of these bonds are pi bonds. Similarly, if I have C double bond C, then one of this is a pi bond. What about the other one? This is a sigma bond and this is a sigma bond. So theoretically, the first bond is a sigma bond and the next one, second or third ones are pi bonds. Okay, cool. Please revise all this. If you're not sure about what I'm talking about, check out my chemical bonding videos. I can link them in the description if you like. So how do you represent organic molecules? You draw all the relevant bonds, right? This is the complete and expanded way of doing so. So you have ethane and propane. This is 10 standard stuff, right? CN, H2N plus 2. Yeah? This is that standard formula. Now, I can also write it in another way. You can draw a line diagram. Sort of a 3D sort of representation. I mean, in three-dimensional space, if I were to draw one of this carbon, which is this first carbon, say here, it's going to have these three hydrogens and then whatever that chain is behind it, right? So this is a tetrahedral structure. This is what I've drawn over here. Okay, expanded all of this, drawn all the hydrogens. And interestingly, you can see that the next carbon, which is say this is C1, this is C2, this is C3, right? The second carbon, I've drawn the hydrogens in a different configuration. We'll study that in isomerism, okay? You can check out conformers and all of that later. But this is the way it's done. Now, all of this is a little crowded, so let's contract it further. And this is my favorite way of representing organic compounds, the line diagram. Why is this awesome? Because it communicates the information without you having to draw all the hydrogens all the time. So this is the structure we will use the most, and you'll see that it's extremely useful when you study isomerism. Okay, so this was a general alkane. I can also do the same thing for an alkene. You have C2H4, C3H6. What is this? This is CN, H2N. Again, 10th grade stuff. Now, if I were to do this using the line diagram, this is how both of these would look like. I can keep expanding this. So for example, what is this compound? I have 1, 2, 3, 4, 5, 6. There are only single bonds here. So this is going to be hexane. What about this compound? But I'll put a double bond say here. So 1, 2, 3, 4, 5, 6. So this is going to be hex 3 ene. Why 3? Why not 4? Please revise nomenclature. Okay, I'm not going to be doing that unless, I don't know, like 100 of you ask for nomenclature. You can figure this out from NCERT. Okay, all right. How would I represent it? This is how, with this line diagram, as I told you, my favorite way of doing things. Okay, we're going to shift gears. This is a basic introduction, maybe not relevant to the rest of the session, but still important to know. This part, this representation part, very relevant, you'll see. I'm going to quickly revise formal charge, okay? Why? Because using this, you'll be able to figure out a lot of things in resonance. What is formal charge? Well, total number of valence electrons on an atom. Valence electrons, what's valence electrons? Well, get the periodic table. Remember atomic structure? Yeah, check that video out. Minus, this is in brackets, all the unbonded electrons plus shared electrons by 2. Now, shared electrons by 2. You remember that this is a covalent bond, right? Each of these are basically 2 electrons that we're representing with one line each, right? So I can also write the same formula as valence electrons minus unbonded electrons plus the number of bonds or the lines itself, okay? Quick revision. Again, if you want to do this in detail, check out chemical bonding. Let's find the formal charge of oxygen and hydrogen. There's one oxygen here, 2 hydrogens, both of them are similar. So we can count them as the same hydrogen in terms of formal charge calculation. Okay, so for oxygen has 6 valence electrons, right? Yeah, periodic table, atomic number and all of that, right? It's 8, so it's, I'll do this for the first time. Yeah, 1s2, 2s2, 2p4. These are valence electrons. This is 6. Okay, cool. That's out of the way. Unbonded electrons, how many do you have here? Well, that's these dots over here. These dots showcase the unbonded electrons or lone pairs, but we got to count them separately. So that's 4. Okay, so this is 6. Oops, this is 6. Unbonded is 4. And bonds or lines, which are 2. So I'm going to write all of that together. Look at that. Beautiful. Formal charge is 0. We're doing a revision. So I hope you're good at this. If you find this to be boring, skip ahead about 30 seconds. Hydrogen, same deal. Hydrogen has how many electrons? Well, it has just 1 electron, right? And here how many bonds? Well, 1 bond. And it doesn't have any unpaired electrons or unbonded electrons, right? So this is 0. Pretty stable compound. Why does it say stable? Well, we'll look at that. But if there is a formal charge of 0 on all the elements, then hey, that's a pretty stable compound. Now I'm going to step it up a gear, yeah, because this is what you're here for. What about this cool looking compound? Oh my God, this is so scary. It's really not. This is just another way of writing phenol. Trust me, I'm not even kidding. And that's what we'll end this session with, this video with, right? What? This is phenol? Yeah, we'll see. Hold on. This is not the whole picture. Let's find the formal charge of oxygen over here. How are you going to do that? Well, valence electrons is still 6. Unbonded electrons is going to change. It's not 4 anymore. It's just 2, which is these 2 electrons. Okay. Bonds, you can count lines, can't you? So that's just 3. So oxygen is going to be 6 minus 2 plus 3, which is plus 1. Whoa, really? Plus 1? That's such a strange thing because oxygen is supposed to be an electronegative atom. I'm giving a plus 1 charge? Hold on. This is right. Nothing wrong here. It's perfect. Okay. What about this carbon here? It's interesting, yeah? This carbon, valence electrons is 4, right? Okay. You should be good at this. 2s2, 2p2, yeah? So that's, oh God. Do I have to write that again? Is this too confusing? I really hope not. But if it was, there you go. 4 valence electrons, that's where this comes from. Okay. And, well, I've drawn this. Where this come from, don't worry about it. But this is the real structure. For some reason, carbon has a couple of electrons on top of it. So, cool, let's count that here. All right, sweet. And it has, wait, 3 bonds? I only see 2. Where's the 3rd bond? Did I do something wrong here? This is where the whole line bond things come into the picture, right? I know I've drawn this hydrogen, but you'll notice that all of these also have hydrogens on them. They do. You haven't drawn them, but yeah, these hydrogens exist. Okay. So back to reality. Count that extra 3rd bond, which is why I said it's extremely important for you to understand what this line diagram means. Okay. That's why this number is 3. 2 carbon-carbon bonds and 1 carbon-hydrogen bond. I'm going to write that here. So 2 carbon-carbon bonds and 1 carbon-hydrogen bond. That's why this is 3. Hence, this is minus 1. And what do I do? Well, let me erase these things so it's easy for you to read. There is a negative charge on this and a positive charge on this. You may have seen this structure if you're like, wait a minute. If you're in 12th grade and you've already done phenol, you're like, yeah, this is sort of a resonance structure, one of the resonating structures of phenol. Absolutely. This is the deal behind how you get this plus and minus charge. That's the formal charge itself. Okay, so I've heard students having a huge confusion like, where did this plus sign come from, where does this minus sign come from? That's the formal charge. So obviously the next thing that makes sense to talk about is, ta-da, resonance. Why resonance? You'll see, ties in beautifully. It's so awesome that we're going to change all the way and make it all bright. Oof. Okay, the deal is, some molecules, you can't represent them with a single Lewis structure. What's a Lewis structure? All those structures we drew with those lines and electrons and all that, they're all Lewis structures. Please revise bonding if you're not familiar with this. And if I draw multiple structures that represent the same molecule, all of them are separately called resonance structures. They're all identical. It's just the position of electrons that changes. Let me show you what I mean, right? again and again, this is something you studied in bonding. Carbonate ion has 3 different structures, and this right here is the actual structure. Yeah, these are theoretical structures. Yeah, they don't really exist. Theoretical structures, because you and I can think about it this way, that okay, carbon needs to have 4 bonds. If I have a double bonded oxygen, that's great. If I have a single bonded oxygen, it's the only way it exists is with the formal charge of -1 and -1 here. Why? Because carbonate ion is CO3 2 minus. Please revise bonding if this is all new to you. The important idea is that this is the real structure. Yeah, this one at the bottom right here. And how do you prove that? You make this cool diagram which shows you that these red parts are where electrons are concentrated, and the blue parts are where there are fewer electrons, right? So in a way that the blue part has a slightly positive charge and the red parts have a slightly negative charge. In organic chemistry, you will see a lot of such diagrams. Yeah, they help you see what happens in real life. So this resonance hybrid is real, whereas these things, they don't exist. None of these 3 structures really exist, but actual thing is a resonance hybrid. Okay, this is extremely important. Again, a revision from the point of view of chemical bonding, but very important here as well in organic chemistry. So why do you draw these resonance structures? Well, to keep track of all the electrons. There's so many of them, they roam around, they do their thing, and the goal is that these electrons, they are said to be delocalized, because if there's a path for electrons to move, why will electrons move? Well, if there are empty p orbitals, yeah, usually they can move around with that, and because of this moving around of electrons, they have multiple structures, so there's more stability to this. If you like thermodynamics, it has a little bit to do with entropy. You remember, more microstates, more stability. So in a way, it's similar to that. Don't quote me on it. I'm giving you a very loosely based structure, loosely based idea, but this is the logic. Okay, maybe you have seen this before. Yeah, benzene. It's awesome. It has 6 p orbitals, all of which have just 1 electron, and these electrons are chilling around. They're all sp2 hybridized carbons, right? And what happens is that they have electrons moving around, and this is the calculate structure, etc., etc. You see some of these arrows. What on earth is happening here? This is what we'll try and understand right after this. Yeah, we'll figure out some rules for resonance, and you'll be able to draw these structures, go from one to the other very easily. That's the last thing that we're going to do in this session, so stick around for that. So what are the rules for resonance? Okay, first rule, you can only move electrons around. You cannot move nuclei. If you decide to move nuclei, that's going to be an isomer, no longer a resonance structure. And if you want to study isomers, I've done that in detail on the bento links. If you want, I can also put it in the description. Now I've got a compound over here. Okay, well, it's an ion, sure, but it has some pi bonds, and it has a lot of electrons just hanging around that are unbonded. Okay, which means that there are some empty p orbitals and some filled p orbitals. If this is sounding foreign to you, this concept of empty and filled p orbitals, you need to revise the whole concept of hybridization. Please go through chemical bonding and do that. Okay, so I'm going to move these electrons around. What am I going to do? These colored ones, these red electrons, I'm going to put them in between carbon and oxygen, which means that they're going to form a bond. But if I form a bond here, carbon is going to have 5 bonds, and that's a problem. So I need to break some bonds. So I'm going to break this bond, and these electrons are going to go over here. So let's do that and see what happens, right? And assume that this negative charge exists. I haven't given the reason behind it, but like this is the initial structure that you start with. If I do this, what happens now? This is the new structure that gets formed. Okay. Wow, that was interesting. Do you see what happened here? These red electrons form this bond over here, which is red, and this blue set of electrons that were bonded now become unbonded, and they go on top of this nitrogen. And you'll notice that I put a negative charge over here. Why do you think that is? Hint, hint, formal charge. Okay, but can I go back to this structure? I've drawn a double-headed arrow, which means that I should be able to go from here back to here. Yeah, sure, why not? Let's just do the other way around. These electrons are going to come back here, form that third bond, triple bond between nitrogen and carbon, and then again carbon has 5 bonds, not cool. So then this goes back and forms that. gives the electrons back to oxygen. Let's do that properly and formally, pun intended, and these are then known as resonance structures. Okay, and you'll notice that this negative and this positive charge, or both negative charges, are important too. What's not a resonance structure? These. Why? Because look at this. Here carbon is bonded to nitrogen and hydrogen. Here carbon is only bonded to nitrogen, not hydrogen. So the bonding itself changes, and these are isomers. They are not resonance structures. And remember, I told you that you need to be able to be really confident about this sign. Like, why is there a negative sign over here? You remember what I told you? Formal charges. Let's figure out the formal charge on oxygen. You know the drill. You've got 6 electrons to start with, valence electrons, and you've got 6 lone pair of electrons. Well, 6 lone electrons, unbonded electrons, 6 of them, not 6 lone pairs, 3 lone pairs. That we've put over here. And you've got one bond, one line, which is this right here. Okay, so hence the formal charge is -1, which is what we have put over here. That's the origin of that charge. So you need to be confident about it. And you can guess the same thing happens in nitrogen. Its valence electron obviously is 5. Come on. How? Why? Well, 2p3, 2s2, 1s2. This is your valence electrons. 5, right? Okay. And 4 unbonded electrons and, well, 2 bonds. Okay, -1. That's where these signs come from. All right. So now we are confident about how to form different resonance structures and use the concept of formal charges to put these negative and positive charges as well. So we've been using arrows to keep track of electrons for sure. And you'll notice that all of these arrows have a starting point and an ending point. The starting point is, well, where these electrons or bonds, they come from, and the ending point, which is given by a double-headed arrow, that shows where the electrons are going. Okay, but this is important. If I draw an arrow that has a double-headed arrow, there are 2 over here, I'm moving 2 electrons. I can also move a single electron, that's going to be half an arrow. I'm not even kidding, this exists. I know we haven't come across it, but this is what it is. Okay, another rule, electrons are neither generated nor destroyed. This one's obvious, right? But this one is also really important. Total number of valence electrons, it's constant. You can't change the number of valence electrons, which is why, and look at this, yeah, you should be able to draw this one to this, and this right here, this third one is a little weird. Do you spot the difference? You know how it is, right? Newspaper, you get these things that, oh, what's wrong with this picture? Can you tell me, can you pause the video and figure out what's wrong with this picture? Let's go through the motions. What happened here? Oxygen has a lone pair of electrons. It's got a plus charge. What I'm doing is I'm taking these pi electrons, the bonded electrons from the carbon-oxygen bond, moving it onto this oxygen. Hence, oxygen gets a pair of electrons. Why a pair? Well, both of the electrons move. I get a pair. But then, shouldn't this charge also change? Yeah, the plus charge goes away. Oh, wait, hold on. I've given oxygen 2 electrons, but the charge is only changing by 1. Huh. Why is that? Because, boss, look at this. This bond also breaks, right? This bond had 2 electrons. It breaks. Yeah? If this is seeming confusing to you, why there's a charge of +1 here and 0 here? Go back to the formal charge idea. Get confident as to why there's no formal charge here. You can do that, right? 6 valence electrons, -4 bonded, and -4 unbonded electrons, and 2 bonds. Look at that, 0. And if you do the same formal charge for oxygen over here on this guy, you have 6 valence electrons minus how many electrons chilling? 2. And how many bonds? Well, 3. Formal charge of +1. That's why there's plus here. Ta-da! Get confident of this. Okay. Now we did all this. And if electrons go away from here, then carbon's going to have a plus charge. Please figure out how. Do this formal charge exercise. Now, what's wrong with this last picture? I asked you to pause. I haven't told you what's happening. Boss, look at the number of electrons around oxygen. It's got 10 electrons. You can't have randomly putting electrons away. It needs to have octet and we are good. 10 electrons, obviously not good. How 10? 4, 5, 6, 7, 8, 9, 10. Not cool. Hence, this is bad. Okay? Cool. So, unshared electrons can be moved. Pi electrons can be moved. Resonance seems complicated, but it's a lot of fun. Yeah, you need a little bit of practice. That's the main thing. If you've got a complete octet, by the way, the structure is extremely stable, and that contributes more to the hybrid. So if I look at these two structures that I just showed you, this is more stable, this is less stable. Why? Because if I draw a round around, like, circle around oxygen, you can see that there are 8 electrons here. If I draw a similar thing around carbon, I see 8 electrons. Get confident of that. If I do that over here, carbon only has 6 electrons. How? Because of these bonds, right? Around oxygen, I've got 8 electrons. So this is less stable because it doesn't have a complete octet, okay? This contributes more to the structure. So the structure is going to be more like this. How do I know? Use that diagram that I showed you with carbonate ions, right? To see, oh, in real life, you will see that there's a concentration of electrons in one place and the other. Another really cool idea, if I have fewer number of formal charges or a lower formal charge, that contributes more. What does it mean? Like we saw with water, right? All of the atoms had a 0 formal charge, more stable. If I have a lot of formal charges like +2 or -2, then that's not going to be a stable one. Yeah, this is what this is trying to say. Another important idea, the more electronegative atom, if it has a negative charge, that's going to be more stable. Less electronegative atom, partial positive charge, more stable. Wait, hold up. More electronegative atom. Let's take an example. You remember this structure? Yeah. Between oxygen and nitrogen, what's more stable? What's more electronegative? I think oxygen is more electronegative. Check it out. If oxygen is more electronegative and I'm giving it a negative charge, looks like this should be more stable, and that is absolutely true. This is indeed more stable. That's it. How do you know? Check out the actual electrostatic map that we saw with carbonate. One really common mistake, sometimes people put more than the number of bonds an atom can have. You need to keep valency in mind. If I decide to say, oh, look at that, I've got electrons, let's move them around. Carbon has 5 bonds. Does not work. Does not work. Here are a few examples of resonance examples. Here are a few examples of resonance. We've almost come to the end of this video. Just a couple of really important items. Yeah, this is called a dipeptide. You will learn about this in biomolecules. Do not get intimidated by it, but make sure that you understand how the electrons are moving around, how the formal charges make sense. There's something called the allyl cation. Where did the L go? This is going to be important, huh? This is resonance stabilized. It's got 2 forms, both of them equally stable. What about something called the carbonyl enolate? Is there one form that's more stable than the other? I feel so. Oxygen negative, great. Carbon negative, not so great. So I feel the one on the right is going to be more stable. So when I say cross and plus, I just mean to say stability, right? I'm not saying that the structure doesn't exist. Structure definitely exists, so don't get confused if you're watching this at 2x or you're skipping around. The cross and the cross and right were mainly to tell you which one's more stable. Both of these do exist, which is why this is a resonance stabilized hybrid. You're going to be like towards the end of 12th grade, you will see, oh wow, enolates are really cool. If you're going to be studying organic chemistry that way and you don't give up on it, I hope to see you there. Let's end this with this concept of resonance of phenol. I showed you some formal charges of a complicated thing and I told you that's phenol. I'm going to prove that to you. This is phenol in all its glory. What is phenol? See, oops, let me change the color here. C6H5OH. This is phenol. Yeah. So you take a benzene, which is C6H6, and you remove a hydrogen and add OH to it. So you've got this structure. Okay, that's a benzene ring. And magic happens. I'm kidding. Make some reaction happen. You can do that and you get phenol. Okay. So what am I going to do here? Let's move electrons around. Why is phenol stable? Well, it's resonance stabilized. What happens here? I can move these electrons on top of that oxygen, yeah, that lone pair, and form a double bond. We're like, whoa, hold up. That's going to really mess things up. Hear me out. Wait. Okay. If I do that, this carbon here will get 5 bonds. And we don't want that, right? So we break this bond. That's the most logical thing to do. So let's break that bond and take those electrons to this carbon over here. Okay, the one I put with the yellow dot. So what this does, it gives you a partial positive charge on the oxygen, a partial negative charge on this carbon, which are formal charges. This is exactly what I taught you formal charges with about 10 odd minutes ago, maybe 10, 12 minutes ago, I hope. Yeah, I think you know what I'm going to do next. I'm going to move these electrons all the way around. Let these guys chill. Yeah, this is like status quo. Let them stay. Let's move these around. Yeah, these electrons right over. What am I going to do? I'm going to move them here. Why? Because these electrons on carbon, carbon doesn't really want to have electrons. It's going to give it away. If it gives it away, where's it going to go? I think it will form a double bond here. But we will do that. This bond has to break. Why will this break? This will go here. Okay. Now I think you're getting the hang of this. Let's move these electrons around and get confident about the formal charge business. Okay. Please do the formal charge calculation by yourself. Pause the video, do that. Make sure that this negative and plus charges make sense. I'm not changing this at all. Yeah, the plus charge and oxygen, let's leave that be. And carbon, being carbon, does not want that negative charge. So it's like, bro, take it away. It keeps moving around. It keeps moving around. Okay. You see what happened here, right? These electrons come here. So this forms a double bond. And then you got carbon with 5 bonds. That's not possible. So then these double bond electrons come over here. And just like this had a formal charge of -1, this one gets a formal charge of -1. You know the drill. Repeat these steps and you get another resonance structure. Yeah, this one's going to be drawn right over here at the bottom on the left. Okay. So because there are multiple resonance structures, wait a minute, hold on. Something interesting is happening here. This last step, these electrons that were there over here, you know the drill, right? This happens here, this comes here, you got these bonds, etc., etc. What is happening here? This bond on oxygen also comes back here because oxygen on a plus charge, yeah, that's like not the best either, right? And then it comes back to your good old phenol right over here. Everyone's happy. Okay. So although these middle steps where oxygen has a plus charge and carbon has a negative charge do not seem very stable, but because so many resonance structures exist, it gives phenol stability. And phenol, as you can see, is electron rich at certain positions. You call them ortho and para positions, which will lead to a lot of reactions of phenol, which we'll study later. That was all I had planned for you in this video. This one's slightly long. I hope you enjoyed it. What am I going to do next? Maybe hyperconjugation and all of that. Stay tuned. See you around. If you liked it, subscribe to this channel and yeah, tell your friends about it. Come on to Discord if you want to talk about doubts or share your thoughts on how we can make these videos better. See you around.